What's up, guys? Welcome to Deep Reinforcement Learning Unit 5 from Hugging Face. This was an exciting week. We covered Unity ML agents. So today we're talking about Intro to Unity ML agents. So, quick introduction. The Unity engine is a powerful tool for creating 2D, 3D games. As you can see, we have like a 2D game right here and a whole bunch of other 3D games. So far in this course, we have done a whole bunch of Atari. We've experimented with different like Space Invaders, and the last unit we did like a Flappy Bird looking thing, 2D. So we've been limited to 2D, but now we're entering a 3D environment. So definitely going to be a little bit more complex. Well, obviously because we have now another dimension with variables to consider. And what does that mean for us is that we are going to have to be a little bit more kind of prescriptive now that when we're training our reinforcement learning agent. So we use the Unity ML Agents toolkit, which extends the capability, allowing us to train AI models within Unity using deep reinforcement learning. It's developed by Unity Technologies and caters to both beginners and experts in AI development. I'll tell you from firsthand experience that, and I would say I'm more definitely on the beginner side and learning about reinforcement learning, but knowing a little bit of Python and going through this entire this unit's coursework, it made things really click, and it was really cool to see the product of what we've been doing. So definitely more fun to watch your agent after it's been trained and it's like a beast, better than you at if you tried to play the game manually. Like a lot of the times, the agents you're building this week, they're going to do a better job than you can. So it's kind of like that same kind of feeling that I assume DeepMind had when they finally beat AlphaGo. So even for beginners, was very easy to use this Unity ML agents, and it was really cool to watch after the fact. Definitely had some big aha moments here. I feel like I definitely leveled up in my understanding. So what are the key components of Unity ML agents? This is a quick diagram. You can see we have this learning environment. Within the learning environment, there's a communicator, which is connected to something outside of that learning environment called the Python API, which is connected to the Python trainer. So a little bit about the little pieces, the learning environment. This is the Unity scene with all the environment elements. This includes your character. It includes like other objects in your scene. It includes like the boundaries of the map. Things like that are what comprise the learning environment. Next, we have the Python low-level API, which is the interface to Python interaction. You'll see you see C# here. So external communicator right here communicates externally, connects C# and Python API. So Unity is a C# language, and obviously every time we've trained an agent, we've used the Python language to train our reinforcement learning agent. So intuitively, it makes sense that there has to be some kind of like translator, if you will, that will take those params or parameters or variables or just values in general, any type of data, any data type, any data structure. Predominantly data type is correct nomenclature, but take that data type and convert it into Python speak. So I know I learned Python first, but I got only a very beginner basic understanding of Python. I actually fully learned the React, Perm stack, JavaScript, and later on Next.js, which is my favorite full stack web development framework. And I've heard numerous times that C# is a good follow-up language compared to JavaScript. And even with these different languages too, JavaScript in JavaScript world, you call an array, but in Python, you will call it a list more often than you'll call it an array. So just they all mean the same thing, but for some reason, the different languages, they prefer to use one term over the other, and that's some of the intricacy, the nuance, and like between the different programming language cultures. So obviously, with that, there's going to be different like syntax. Like I actually have no idea about the syntax in C sharp, but if it's anything like JavaScript, which I've been told that it's going to just look like a different version of Python. Like Python is very readable code, and same with JavaScript, but they're kind of just swapping things around here and there. Next, we have the Python trainer. This includes the RL algorithms like PPO and SAC. Haven't heard of SAC before, so hopefully we'll learn about that. But we do know PPO is proximal policy optimization. Not really mentioned, but also part of the Unity ML agents library is this gem wrapper, which is for the OpenAI gem compatibility. This is a really, really cool, like I love this package, this library, because we all know the company OpenAI, ChatGPT, and they really are like top, even technically, this is top tier talent. If they're managing this powerful reinforcement learning library, deep learning library, you know that these guys are like the tip of the spear, so to speak, when it comes to AI engineering. Very cool to see. And lastly, for the petting zoo wrapper, we would use that for multi-agent environments, which I think we will be covering in a later section. So this will be really fun, really cool stuff. And again, this is the environment, the diagram. So you may be wondering, how do you train agents in Unity? What's different? In Unity ML agents learn through a loop of receiving a state, taking an action, receiving a reward, and then moving to the next state. Nothing new here for us. We all know that this is the reinforcement learning loop, and we're just applying that to the Unity environments. The goal is to maximize expected cumulative rewards. Agents are equipped with a brain that determines actions based on the given state, guided by an academy that orchestrates decision making. So it determines actions based on a given state, cumulative rewards. We have seen a lot of this language before. Reinforcement learning, what I've seen so far is that, and especially in this course, this unit is that you really have to get over that initial hurdle, but after that, there's a lot of kind of you can apply that knowledge now. That's really what we experienced in this week's course unit, or week's unit, because the reading was not too long. It was pretty short, pretty condensed, and you get to just train an RL agent to go play some cool Unity game-like environments and also learn while you're doing it. So this stuff is awesome. The first environment we train in is the Snowball target environment. Very cool. You can see we have this bear character and this target that will just randomly spawn. The objective of this is for Julian the bear, aims to hit as many moving targets with snowballs within 1,000 time steps. So trying to get a high score. That's what makes this a game. We want to have the best agent. I know I do, and hopefully you do too. So what are the constraints and limitations? What is this environment that we're operating in? One of those rules of this particular environment is that there's this prevents constant shooting, where we require a 0.5 second wait time between shots. I think intuitively you could see that if there was no like cooldown, this bot would just spam the whole time and get a whole bunch of scores. But now you have to be a little bit more precise because you have that time frame. It's going to end soon. You don't want to just miss a shot because then you have to wait and you're not going to get a high score because you're on a limited time frame. You need to be accurate and precise. So what I liked in this unit is that you really do have to go a little further and think about your environment you're operating in when you're defining your config file, your hyperparameters. So that's very interesting to see that we get to focus more on how do we get our agent trained in a way that reaches our goal in an optimal manner. So observations. Utilizes raycast and a Boolean for shooting permission. Obviously the reward, you get +1 when the agent Snowball hits a target. But when we're talking about raycast observations, this is kind of what it looks like. So under the hood, we all know that like reinforcement learning is just a bunch of numbers and finding patterns. And when you introduce a neural net, that searching is much more effective. That's searching for the optimal action to take in a given state. But what is the state? What is observation? We can see that we have these raycasts, which are like laser beams. They have a magnitude for how far they are until they reach the end. And they also have this angle. So we have a vector. And if we compile a bunch of these vectors and we know like where our target is or where the bad stuff is or where the good stuff is, then that we can see how we may be able to train an agent that's able to take those maximally rewarding actions as opposed to other ones. So very crazy to see. I just had this crazy math visualization. The numbers, they were showing up on my head. And specifically in this game, we have one set of back raycasts, which detects like the boundary. And then we have 3 sets of front raycasts that detect one set to detect snowballs, one set to detect targets, one set to detect frontier, the rocks and invisible walls. So the border where the target is and where the snowball is. And these are the actions you take in that environment. Very simple. You can go up, down, left, right, and you can shoot. And then with that, you train an agent to go as fast as possible and hit the target. I'll walk through the notebook at the end. So I'll move on to the next environment. The pyramid environment project was also a very cool one to watch. Just check some training real quick. This one is not training. Alrighty. Yeah, just so move it back. The pyramid environment is freaking cool. I'll get it ready in the background. I just pulled it up. The objective is to train an agent to spawn a pyramid by pressing a button, navigate to it, knock it over, and retrieve a gold brick. If it sounds complicated, it's because it is pretty complicated. So I'll pull up a random user's one, Zero Sunfire, and just pick that one. Yeah. So this is the game. This is someone else's reinforcement learning agent playing the game. And it first has to find the switch. That's the first step. Still looking. Remember, underneath the hood, it's raycast. This thing is shooting lasers to try to find the stuff. It's like looking, it's searching. But we all know it's probably in that bottom middle piece, but this guy is not checking it for some reason. Wow, this is like the dumbest agent I've seen. Very low curiosity is one of the concepts we learn. Boom. So there you have it. Go and touch the trophy, the green block, the reward function. For this environment, the reward function is already set. We have to just set the hyperparameters and fine-tune it. So it's a mix of extrinsic rewards for task completion and intrinsic rewards, curiosity for exploration. For that agent, we have this negative reward, negative 0.001 for every step. Given this negative reward for every step, we'll push our agent to go faster. And we have a +2 for moving to gold brick. So you can see we have a negative reward and a positive reward. So negative reward makes us go faster and makes sense, and positive reward is what we're trying to aim for, to maximize our cumulative sum of our cumulative reward. Observations. So this one's complicated. 148 raycasts detecting objects, switch state, and agent speed. That's a whole bunch of raycasts that detect blocks, walls, goal, switch on, switch off, and stone. So a lot of different variables, very complicated procedure. This environment definitely, I think it took 40 minutes for me to train my model on, and I couldn't show you here because I don't know. I think the upload feature is broken right now or something like that. But yeah, all is well. Then action space, we can only go up and down, and then we can rotate left and right. So these were the only two. This example, this environment plus the Snowball environment were the only environments we trained on this week, and it was really interesting you had to mess with the parameters a little bit to get a better score, and it's good to see like what we're learning and like from the previous lessons coming into today's unit, that progression of our own reinforcement learning and learning reinforcement learning. Very cool. So one of the optional topics is curiosity in deep reinforcement learning. This diagram kind of shows a great example of curiosity. If the model is not curious, if it's not like exploitative enough, like independent of exploitation versus exploration, and yeah, I said exploitation, I probably meant exploration earlier, but independent of that, there's a concept of curiosity. So sometimes you still want to go take random actions if you get closer to a place that doesn't have your in previous training runs a reward. So if that is not the case, you'd have this scenario where you would potentially not get the armor, even though you're at 0% armor, by just roaming around, not going aimlessly. And curiosity-driven learning addresses the sparse reward problem by generating intrinsic rewards for exploring novel states. It encourages agents to explore their environment more thoroughly, improving learning efficiency. Curiosity can be calculated through the error in predicting the next state or using more advanced methods like random network distillation. The intrinsic motivation mimics human desire for exploration and discovery. So beginning of the game is a familiar state, easy to predict. Intrinsic reward will be low since the state at the next time step is going to be pretty easy. However, if you find a new room, it'll be hard to predict, so the intrinsic reward will be high. So basically, you get more intrinsic reward in new states, novel states. So some tips for successful training. In the training, they already give you for successful training in the context of today's lesson. So they already give you a preset list of hyperparameters. I have Unit 4 open right now, but for the Unit 5 ones, you just edit the hyperparameters. And what you would do is you can start off with them. I recommend it. I did that. The first time I just tried changing things up already, but I didn't understand what like a good baseline already was. So I kind of wasted time by training it and trying to set hyperparameters a little too early. It's kind of one of those things. Like even when you're fine tuning things, you don't want to like optimize too early in the process. So letting it just run will set the baseline, and obviously the Hugging Face team probably set it up that way for a reason. So the second time for the second environment, I just let it run the first time, and it had a pretty good result. But then I wanted to try to see if I could beat the score, and I was able to because I iterated on what I observed after the completion of the last training run in this next training. So the next step is to experiment. You're going to have to test different reward functions, and you don't write the reward functions in this week's lessons. You just adjust the hyperparameters, and then so test different hyperparameters and observe the impact on agent behavior. Pretty intuitive. You need to iterate, basically. Continuous learning. You need to continuously advance your knowledge by exploring more complex RL concepts and Unity's advanced features. So more so for in the future after this work. But one of my big tips, and this is inspired by things like Dr. Eureka research paper that just came out where they trained They trained a robot to operate, like they trained a robot in like a game environment first, and I even believe it was Unity, and then took that same model and put it into a real life robot operating in the real world, and it's able to do crazy things like balancing on a ball when it has not been trained to do that in the training environment. So very cool idea. And the idea is you can use a large language model to write a better reward function than humans can, because no human was able to do that, or wasn't able to do it as fast as GPT-4 did, which is what that video showed. And I translated that to the same thing. Like for this week's unit, I had OpenAI, my own personal AI, try and tried to prompt engineer for better hyperparameters, and I kept on sharing what I observed, the scores I got based on the hyperparameters that are suggested. And I iterated on that, and I keep getting higher and higher scores. So it's very cool to see that I can just share what I observed and what I'm expecting, like, or what I want, which is to have a better, higher average score. And even like the highest score I was able to get was a 41, but you can see there's still a lot of variation here. So I want to get like something a little bit more predictable with not as much of standard deviation, so that like it is over a long period of time, generally more higher of an average score. Kind of a mouthful, but that to me is more stable and more reliable. I wouldn't want something that's erratic and gets super high scores one run, super low scores the next one, depending on the environment, because like the world we live in, it operates in a dynamic environment. We want to be prepared for that, and our agent should be as well. So iterate with ChatGPT to get optimized parameters. In one of the earlier sections, we are encouraged to use Optuna, and I decided it was an optional course and I didn't try it at all. But I probably should, and I should go and compare the results from using Optuna compared to something like just prompting OpenAI or your own local large language model. So you try this out. Use an LLM for config optimization. My mind was blown when I did. And then additional resources when you're done. Check out the Unity ML Agents GitHub for documentation and code examples, OpenAI Gym to learn more about the Gym interface, and some more PyTorch tutorials to enhance your understanding of the RL algorithms used in training agents. So I'll just briefly talk about the hands-on portion for this week. So they do a good job of explaining everything that's already in the material. Obviously, use your GPU, but you go and clone the repo, go inside the repo, install your dependencies, get your environment ready, and then you go set your config file and make some edits to what you see fit. And then you just go let your agent run. After that, you push it to GitHub and you kind of repeat the process. And a lot of your time will be spent on changing things in your hyperparameters, like how many steps do you want to do? How long is your time horizon? What's learning rate, batch size, buffer size, beta, epsilon, lambda, number of epochs. So yeah, the same goes with the next environment. You kind of learn it a little bit. Download everything, and you kind of just iterate on your settings. So you can go and edit the config for max steps, but you can go and experiment with different config files. So if I seem a little tired, I am. We have these weekly study sessions on Thursdays at 10 a.m. And for some reason this morning, the audio was just inaudible. You couldn't hear. So I'm going and re-recording this because I know that there's hopefully someone out there that will watch this find it useful, because I'm not an expert in reinforcement learning yet, but I'm at least one chapter ahead, and I'm trying to share what I've learned to you, for like numerous reasons. Like, so if you're watching this on YouTube, I'm looking to connect with you. I'm looking to connect with people that are interested in reinforcement learning. And if you're part of the group study and just couldn't attend because of timing reasons, this video is for you too. I'm wanting to make sure that I keep recording this because I know some of you guys can't make that 10 a.m. meeting, whether it be for work or other obligations. So still wanted to record it despite not being able to record it properly earlier in the day. So I hope you enjoyed this. Stick around for next week. And if this is your first time watching, come join us next Thursday at 10 a.m. Eastern. Details in the description below.